Today we're going to begin our module on ordinary differential equations. More precisely, we're going to talk about starting from motivation, why, what are they, why, and the basic answer is they are very useful in helping us model physical phenomena. We'll talk about different concepts such like as the initial value problem. We'll learn how to recognize different types of ODEs and systems of ODEs. We'll learn how to identify the independent and the dependent variables and talk about different types of ODEs. So first of all, what are ordinary differential equations? An ordinary differential equation is an equation where the quantities we're interested in, for example, the relationship between the dependent variable and the independent variable, are expressed in differential forms, in other words, with derivatives of the function of interest, right? So we are interested to find a solution, which is a function y of x, a function of y, the dependent variable, x, the independent variable, that if we plug in this into both sides of this equation, the equality holds, right? So any curve, any function y of x that satisfies this equation is what we call the solution to this ordinary differential equation. We'll talk about why the name ordinary in a slide a little bit later on. But here's an example of a differential equation. Let's say y prime equals y of x plus x, right? And just as a side note here, when we say y prime of x, what we mean is dy of x dx. Right, so here's an equation. It's an example differential equation. So if we can find any y of x, any that we plug in this right-hand side and the left-hand side, of course, in the left-hand side we have to first differentiate. But if this turns out to be equal, then we call this y of x the solution to this differential equation. Right, so if we start thinking of this graphically, right, we have the independent variable and the dependent variable. So we have the x and the y variables over here, right? And this is saying that for any x and y, we have the derivative of y of x is given. So let's say we go to a point here, somewhere here, and we have this point, let's say 0.5 on this axis and 0.5. We plug in 0.5 here, right, and 0.5, so we have that y prime at this point here should be 1, meaning the slope of our solution should be 1. And this is what this vector here is a slope 1 line, right? So this vector is slope 1. Likewise, if if we go to, let's say, the point 0, 0, 0, right? So the slope here should be 0. There should not be any slope, and indeed you see that the slope of this line here is 0. So in other words, what the differential equation is saying is talking about, in this case, in this particular case, the way that we're written, it's talking about the slope of the curve, and it's not giving you the curve, the solution to the curve itself. Rather, it's giving you an explicit form for the slope of the equation. Right? So in some ways, when we find a solution, we have to find the curve whose slope satisfies this equation. So, and this process will depend on where you start, and this is the meaning of an initial value problem, right? So if we have some starting point, which we call x naught and y naught, and y naught is essentially y evaluated at the x naught point. So we choose, some x naught point here, and some y naught that corresponds to the initial value, which we don't know. So this has to be prescribed, right? So this will be a given. A problem setup will be given. You're given x naught and y naught, and then you're asked to find the solution. So if we start, for example, here at this initial point, this initial value, and let me choose a different color. So for example, if we start here, then we understand, we compute the slope, right? We plug in x and y, and we get the slope. So we know at this point the slope should be pointing in this direction. So we might as well take a small step in that direction and reevaluate once again the equation of the line or the slope, right? So, and in this case, we obtained the slope. So we keep progressing in this strategy, right? So this is one way to interpret what we're going to talk about in this video, which is to try to find the solutions numerically by starting with a point and then following the slope where the slope leads you. But the point in this slide is to try to make you realize that it will matter where we start. So for example, if we started over here, instead, now we're starting this slope, we follow this slope, we follow this slope, right? And pretty soon, we'll see that if we start here, we'll get this curve. But if we start here, we get this curve, right? And if we start here, we get this curve. If we start here, we get something else, right? So the equation by itself doesn't specify a unique solution. To specify a unique solution, you need the differential equation plus the initial values. And this is what is known as an initial value problem. Sometimes we abbreviate this by IVP. And the goal in this video will be to do exactly what we've done in this picture. We start with a point, an initial value, and we compute the slopes, and we just follow along in this vector field according to the slope. Why are we interested in doing this? Why do we want to learn numerical methods that can give you the solution and allow you to plot it in a computer? The short answer here is it's a very important technique in modeling physical systems. And here I have several examples of physical systems that can be modeled by ordinary differential equations. Starting from the spring and mass system, where we're interested to know the position of this mass as a function of time, and through the balance of force technique, we can understand this position as a function of the velocity and acceleration of the position, right? So in this particular case, here's the differential equation. It's given in terms of y double prime, so two derivatives of y. So we don't have y itself. We have just an equation that y must satisfy so that, you know, this mass will be on the spring. And again, the system will oscillate. If you start it with a slightly stretched value here, the system will go up and down, and eventually decay. If there's some friction, it will decay to a steady state solution, right? But the laws that govern the motion of this system here are expressed in differential equation form. If you look at a vibrating string, a violin or guitar string, there's another differential equation, right? Where here's the wave, the amplitude of the wave is given the y, time is the time variable. You can see that there is a differential equation here that is not giving you y directly, but again, it's giving a function that y must satisfy, including derivatives of that function. You can model waves with this approach. You can model electric circuits that include an inductor, capacitor, and a resistor. So for those of you electrical engineers out there, you'll be learning how to write an equation for this particular circuit, and this equation will be exactly an ordinary differential equation. If it's a circuit of this type, this will be the equation where the values for inductance, resistance, and capacitance and the electromotive force are also given here. You're given this equation and you're asked, what is I, right? What is the current over the circuit? We'll actually look at this later on the slide. If I want to model what happens to a mass, for example, if I'm throwing a stone from the top of this tower, what happens to the height of the stone as a function of time? We start from a differential equation, an ordinary differential equation that says the acceleration, the acceleration is approximately constant on the surface of the Earth, and from that assumption we can derive the whole thing. velocity of parachutes, the water level on a tank, the formation of a beam, the pendulum equation, predator-prey models, COVID-19 epidemiology models. All of these applications involve obtaining the solutions of ordinary differential equations. So how do we solve ordinary differential equations? There are a couple of methods, and in the differential equations class, you would actually go through a variety of methods, the recipes that one can use to try to solve these equations analytically using pen and paper and derive the solution, which is not what we're going to talk about here, but it's good to review some concepts. So the basic technique for solving ordinary differential equations is what I loosely call guessing. Right? So there are some systems, for example, y of t equals y naught e to the kt, right? This is a famous equation for which we know if we differentiate this with respect to t, we get this over here where the k essentially comes out. And so since this part is already y of t, so I might as well replace y of t in here, so I have ky of t. So here's a differential equation that can be expressed, and we know the solution to this differential equation is given here. And this is the famous exponential growth or decay system. Anytime you see something like this, you know the solution is given, right? Once again, in order to specify an actual curve, you need to start with an initial value, or in other words, you need to state an initial value problem. Here we have many different initial values for exponential growth and many initial values for exponential decays. Another, perhaps a more robust way to solve differential equations is the so-called separation of variables techniques. Right? So the idea here is that you take your independent variable x and the dependent variable y, and you put the independent variable on the left-hand side and the dependent variable on the right-hand side. If you're able to isolate one variable to one side and the other variable to the other side, then if you're able to write this equation in this form, then all we have to do is integrate this side and integrate this side, and right, so we separate the variables first, then we integrate both sides, right? And this is just a simple function of x. Sometimes you're able to integrate this way, and this is you can apply the change of variable techniques to rewrite this as a simple integral of y. And here you go. If you can solve these integrals, then you find the solution of this differential equation. Here's an example, right? Let's say our ODE is pressed here. Y prime is 1 plus y squared. This is a separable equation because I can take this to this. So first, I can write y as y dx, and then I can take this, put the dx to this side and this to the denominator, and here is my separable equation, right? So if I integrate the side, I get arctangent of x. If I integrate 1 here, I get x plus a constant, right? Or we can just rewrite this as over here, right? But here we had to get lucky here really, because the equation had to be easily separable, and we had to know what the integrals on the left and right hand side are, right? So let's look at the differential equation here. Let's look at this problem of solving for the height of a stone as a function of time, starting from Newton's law, right? That says that the acceleration at the surface of the Earth is relatively constant, so y has a mass, so that the differential equation is stated here. So we'll write it up there again. So this is y double prime of t, which is acceleration of that stone, equals to g. G is minus 9.81 meters per second, as we learned in basic physics class. So if we integrate this function once, right? So here we have this inseparable form, right? There is no y on the side, and there is there is no x on the side. So we have or no t, sorry. We have then that the integral, which will be y prime of t, will be g of t plus a constant, right? This we learned from basic calculus, and we can call this constant v naught. Why v naught? Because this will be our initial velocity, right? You can, for example, you can just drop this rock or the stone, in which case the initial velocity will be 0. This will not be there. Or you can throw it down with some initial velocity, right? So the velocity of our particle or of our mass will be given by this equation, right? Depends on whether I just drop it or I throw it. Perhaps I throw it up, right? So it could be a negative velocity in this sense. We then repeat this process and integrate this again. So we have y of t will be 1/2 g t squared plus v naught of t plus y naught. So now what is y naught? Y naught is the initial height, right? So we can we have to write this here as y naught. So here you have a quadratic function that spells out, that gives you the position of this mass as a function of time, given that you know the initial height and the initial velocity. Again, this was derived from Newton's law, which is essentially an ordinary differential equation. Here's another example, right? Let's say we have a water tank that has an opening at the bottom, right? And we would like to, and we start with some level, water level at some known starting time. Time equals 0, is as good a starting time as any. And there are some well-known laws as to the velocity of the outflowing water, and this is known as Torricelli's law. And so, and height is the water height as a function of time. So here's an equation, and we can of course obtain the area of the opening of the hole to compute the change in volume. We also have that the change in volume is given by the cross-section of the tank. So we equate this change in volume with that change in volume, and this is delta H or delta T. We take the increments of delta T towards 0 and do some rearrangement, and we can write this equation here, which dH dt equals H on the other side. So this is a differential equation. You do a little bit more work, and you can arrive that the solution of this differential equation here, H of t, is given over here on this side. So once we have this, then we have the starting time. So we also, for the initial value problem, we also ask what is this, and if we know this, we call this H naught. And once we have this, this will be our IVP, initial value problem. Once we have the initial value problem, then we can plot the entire solution, and we can find out exactly what will be the time where the water tank will be empty, for example. So here's another differential equation, ordinary differential equation that governs another physical system. Just the last one, right? So we mentioned already circuits can be modeled by differential equations, and you use Kirchhoff's law to add up the change in voltage of all these components, starting with the electromotive force, the change in voltage of this component, they have to add up to the same thing. Of course, the change in voltage for inductors taken with respect to the first derivative of the current. The resistance is the taken just resistance times the current itself. But this is a differential equation, right, where the independent variable is t and the dependent variable is the current over the circuit. We do a little bit more work, and we're able to write the solution for the system, which once again, you need the initial value to actually plot one. But here are some possible solutions that you may have. So, this is a summary of many applications. Another application that is particularly important in biology and medicine, especially these days, is what we call these compartmental models. So this is a sort of like a loose term to define a unit. It's like building Legos. If we understand the Lego piece really well, we can learn how to connect them and how to put them together with other pieces. So let's say we have a compartment here. The compartment may be, for example, the volume in a tank, like we just talked about, right? And we may have some K in, which will be a constant that describes the amount of this quantity coming in. Maybe this is in milliliters per second, right? Depending on the system, there will be different physical laws that will give you the value of an equation for this K in. And we have our K out, which in this case will also be milliliters per second. And we can express that, the differential equation that governs this particular component will be dv dt, the volume over time, change in time, will be equal to plus k in minus k out. Of course, different systems will have different equations for these things, and we'll substitute this. But this is the fundamental, equation for a unit, a compartment, like we just talked about. And there's many applications in this. Epidemiology is one of them. Modeling chemical reactions for drugs, enzyme ligands, mass transfer, blood flow, and many others. So here, let's look at this particular example here, right? And this is something we're going to see a little bit later on as well, where we're talking about an epidemiology. This is also sometimes called an SIR model. And SIR stands for susceptible, infected, and recovered, right? So this is where SIR comes from. So let's say we have an epidemic going on, and we have, some knowledge about the rate at which susceptible people become infected. We can call this KI. And we also have let's say a rate, perhaps given in percentages, of at which infected people recover. So we can call KR for the rate of recovery, right? And of course, once recovered, it's the assumption, the main underlying assumption is that you're not going to get infected again. So there is no feedback loop here, right? So this is a standard system where recovered people are immune. So let's write what some of these equations could be for this particular example, right? So we have a set of equations that say ds t dt. In this case here would be minus ki, right? The rate at which people are becoming infected. We'll plug in some assumptions for ki, but let's finish writing the other equations. We also can write that the infected, number of infected as a change in time will be essentially ki minus kr, right? Input minus output. So net change here would be ki minus kr. And the recovery is dictated by a similar equation, but now we just have the input, right? We don't have, people don't become unrecovered, right? So, and this will be just input kr. Right, so the science of deciding what exactly goes into these terms is something, it's not the point to cover here, but we can have a brief discussion. That one assumption we can make for ki is that the rate at which people become infected is some constant. We can call this some alpha constant, for example, times the number of people that are susceptible, but it's more likely that people will become infected if there's a large number of infections around. So one way to model this is the product of the number of infected people, susceptible people, with the number of infected people, right? And that product is like particles bumping in a system, right? There's more opportunity, the more quantity of either type is in here. So and this is the whole point of obtaining the infection rate, this constant alpha here. If alpha is really large, right, the amount of infected people can become really large very quickly. But this is an equation that could go in here, and of course this will go in here as well, right? So, and likewise we can assume a model for the recovery constant rate, which could be simply another constant beta times the number of infected people. So let's say in a week, for example, X percentage of infected people will recover to the immune state. So with these two things, we can now plug it in here, right? So we can restate these equations. So let's say ds dt will be alpha s of t, right? So this is all function of t, I of t, right? di of t dt will be alpha s of t, I of t, minus beta I of t, and let's say dr dt will be equal to kr, which is just beta I. So what we have here is now a system of ordinary differential equations, right? We have not just one quantity that we're interested in, but we are interested in the number of susceptible people, the number of infected people, and the number of recovered people over time. And that will be a model that can predict, for example, how many hospital beds may be needed in a particular week or a particular month. So that's the gist of why ODEs, why they matter, covering few applications. You know, in your homework you will have some examples where you're asked to solve this, you're asked to set up some equations, and so it's good to become familiar with them. Let's talk a little bit about ODE nomenclature. Right, so the important thing to keep in mind is that an ordinary differential equation is an expression of change in the dependent variable with respect to independent variable, right? So for example, it's good to learn how to identify, right? So an ordinary differential equation is different from, you may also hear, partial differential equation, which is something we'll cover in a few lectures from now. An ordinary differential equation has one independent variable only. Sometimes we call that independent variable x if it's a system of, you know, that it's a differential equation over space, for example. Sometimes the independent variable may be t, right? So here is the y in this case is the dependent variable, and the x is the independent variable. Right here we have c is the dependent variable, right? It's really c of t, and c is the dependent, and t is the independent. A partial differential equation is something entirely different, not entirely, but substantially different, in that we have two or more independent variables. So for example, in this case we have concentration, which could be a function of x and y, or z included. And then we can take partials with respect to x, we can take partials with respect to y, we can take partials with respect to z, and this may be also a system of time, a function of time, so we can also take a partial with respect to time. So that's the primary differentiation between what's called an ordinary differential equation and a partial differential equation. An ordinary differential equation solution is a little bit easier, especially numerically, so as we're going to see. Another concept that is good to have in mind is the concept of order and linearity, right? As it's written here, order is the highest derivative in an equation, and linearity depends on whether the dependent variables are linear or non-linear. Here, power 1 is one way to describe them as linear, for example. Right, so let's look at this first equation here. So we have essentially only one derivative, right? So dc dt here, and we don't have the second derivative. We have just the first derivative, right? So we say that this is the first order, right? So that we've got to know what the order of this equation is. And now we ask, is this dependent variable expressed linearly or not? And in this case, yes, it's linear. So it's a first order linear ODE. Here is a second order, right? Because we have two derivatives. So this is second order. And now we look at the dependent variable. Is it expressed linearly? And yes, certainly it is. So this is also linear. Here is a second order. And again, h here will be our dependent variable, right? So, but h here is expressed as the cubic power. So this is going to be nonlinear. And here we also have another equation, which is first order, because there's only first derivative here. But this is also nonlinear, because this is not a linear relationship on the dependent variable, so this is also nonlinear. This will be important when we start talking about how to numerically compute the solutions, right? We're going to use a programming language and like MATLAB to compute, to plot the value of the dependent variable as a function of the independent variable numerically without having to come up with an analytical expression for, the dependent variable. And the methods will differ slightly if it's the first order, second order, and so on. The other thing to keep in mind as you look at ODEs, right, it's this notion that an ODE, when it's expressed in this standard form as a first order system, and we're going to see how we can convert higher order systems into system of first order equations as well. But it's to keep in mind that what is really being expressed here is how the change of the variable happens over time, right? So it's an expression for the derivative, but that's been given in the differential equation, that's given explicitly. So you can plot this change in time explicitly, right? So here's this example. When dc dt is constant, that means that your solution will look like a constant. I mean, the velocity, the change will be constant, right? Which if we integrate, it will become a line. Of course, we don't know where this line will be here, right? For that, we'll also need the initial value, right? It could be here, it could be here, it could be here. For that, we'll need the initial value. But this is all this equation is saying, right? It's saying that the change, and better label my axis here, t in dc dt, this is what we're plotting. Here we have a slightly different situation, where now we have that, let's label this axis again. That this is the value of c here, is the change in c is given by c itself. So this could be, for example, a slope, right? This will be a regular slope. This, for example, could be here if the initial value points to crossing here. It may not be, right? But this is sorry, I mislabeled this axis, didn't I? This should be c here. This is what we're plotting, not time, right? So this function here as a function of c, so we can consider the c to be the independent variable and this to be the dependent variable, so it becomes simpler, right? So that's one way to look at things. Here is another way, another type of equation. We can also plot the limiting behavior of this equation. This is saying that, if we take c to go towards infinity, for example, then 1 plus infinity over 1 plus infinity, this limit is going to converge to 1, right? So the value of the derivative of the function should converge to 1, right? So this is what we're going to look at, something like this, where here we have 1, right? And once again, this is C, and this is dc dt. So this is just a summary for you to start getting a flavor of what these differential equations mean, right? Once again, you can view this as a plot of a dependent variable versus an independent variable and start getting a graphical intuition for what these equations mean.